So, good morning, hello, and welcome back to computer graphics. And let's finish the last few lectures online. Quick note about the exam. Yeah, I now confidently have the list of exam participants, and as promised last week actually, this week I'll finally post that schedule. Had to do some rescheduling, so that's why I didn't make it last week. So much about organization. Well, now let's finish the last lecture on rasterization, and this is about where we stopped the last time in presence actually. So we're kind of marching down this rendering pipeline and approached at well, sort of the end of the vertex processing, and then the rasterization will be next, and that will be followed by the fragment processing. Okay, so one thing that I mentioned last time is that traditionally lighting is part of the vertex processing stage. That doesn't mean that we have to do it today, more on programmable shaders later today, but nonetheless, let's just repeat what this lighting thing is all about and what this shading thing is all about. And here again, I want to mention that lighting has very little to do with lightning, and shading has very little to do with shadowing. So not to confuse these two terms. So today will be a ton of repetition from previous lectures. So first of all, just again a reminder: how is information stored? How is information fed into the rendering pipeline? It's usually part of the vertex stream. So anything, be it the coordinate, of course, but then the color, a normal, texture coordinates, those are all parameters that go along with the vertices themselves. Okay, so for position, I guess that's pretty obvious, but there's things such as a normal that you would potentially expect to be a parameter of a polygon rather than a point or a vertex, but I've motivated this before, where this idea comes from, that we're usually trying to approximate something that is non-polygonal, and then it makes more sense to have also parameters such as the normal as a vertex parameter that is then interpolated across the primitive. So another thing that I've also explained before is, what does it take for a lighting to be computed? Well, it takes a couple of parameters on top of the vertices. For instance, we need to know where the light sources are located, what type of light sources they are, what color they have, and there's a couple of other parameters for surfaces, for surface color, such as the reflectivity. I don't want to talk about this all over again in very much detail. You know that there's light sources such as point light, directional light sources, spotlight, so on and so forth, or area light sources as a very special type of light source. But just keep that in mind, that this is that all of this is necessary to compute lighting. So how can we compute lighting? There's a multitude of different ways to simulate real light object interaction, but in particular in rasterization, a very popular method is the Phong illumination. And again, you see that the repetition as well, and hopefully you remember the Phong illumination explanation. So the idea of Phong illumination is to simulate light as a three-component thing. So that light is made up of three essential components, and that is not to be confused with Phong shading. Again, invention from the same person named Phong, related but not the same. Okay, so what are these three components that make up the Phong lighting? They are the ambient, the diffuse, and the specular component. And again, all of that shouldn't be new. Let's look at the diffuse component first, which is really the only component of the three that is physically correct, accurate. So if you have a diffuse surface, you can compute its reflection simply by taking the angle between the normal and the light direction into account. Okay, so basically we wait incoming energy, incoming radiance, by the angle between the normal and that incoming direction. And then it basically gives us the quantity that arrives on the surface. And the motivation, you can still see this here on top. Let's just repeat this briefly. The motivation is that the higher the angle is, so if you go from 90 degrees, where the incoming light direction is collinear with the normal, okay, so when you increase that angle up to 90 degrees, which is kind of the maximum reasonable angle, otherwise you're below the horizon. So if you increase that angle, then your energy that was sent out by the light source is spread over more and more area, leaving less and less energy for each point on the surface. So with increasing angle, the energy that arrives at a specific point is decreased, regardless of the fact that the same energy was sent out by the light source. So, and then this energy that is received is then reflected or absorbed by the surface. So that's the first thing we always need to take into account, is this angle between the normal and the light direction. And then we need to figure out, okay, how much of the arriving energy is reflected and how much is absorbed. And for a diffuse surface, the basic idea is pretty straightforward. We simply say, okay, well, the energy that arrives is just reflected the same in all directions. Okay, so there's no specific characteristic of the surface that it reflects things, for instance, more into the direction of direct reflection, but it just spreads out energy all the same. So then all that's left is that we have to weight that incoming energy by some factor that distributes it over the hemisphere. And we simply decided to call this rho, or a little bit more technical in the rasterization equation, we simply say that's a scaling factor that we call C here. So that's kind of the color of an object, right? If an object is red, if it's dark red, it means that it absorbs everything except red. So this kind of reflectance factor and the color of an object are treated the same in this particular equation here. And then we need to take the color of the light source into account. So we get color of the object times color of the light source times this cosine of this angle, which is equal to the dot product. And that's really physically correct. I've given you examples, actual photographs where you can see that. So that's factor one. The trouble with this one, despite that it's physically correct, it only works well for diffuse objects. So we consider two other factors as well. And one is the specular illumination or specular lighting factor. And the idea here is that, well, there's a number of objects that are, well, specular, shiny, mirrory, whatever you want to call it. It's all kind of the same idea. And what does it mean for an object to be shiny? It means, well, depending on the angle, depending on the viewing angle, you get a different intensity. So if I fix the light source here in that example, for instance, I fix the light source incoming here from the left, and I change my viewing angle. Okay, so if I look in this direction, I see a relatively bright point, and then if I increase the angle from this perfect reflection angle, if I increase this one way or another, the energy drops. So I see lesser and lesser. It's just like a mirror, for instance. For a mirror, I would see a very quick decrease. So I only see the light source when I look at the surface, when I look in the mirror in this perfect reflected direction. And this is what this lobe here depicts. It basically shows you how the energy decreases with increasing angle. Okay, so the question is, how do we model that? Different objects have very different characteristics here. And one idea to model that, and that's exactly Fong's idea, is to model this lobe, this decrease of energy, to model that as a cosine to a certain power. Right? So the power is something that we can choose in any way we want. And what cosine are we talking about? Well, we're talking about the cosine between the viewing direction and the reflectance direction. Okay, and then we raise that to a certain power. And again, it's all repetition. We raise that to a certain power to make this cosine narrower and narrower. So this is what you see here in this graph. So it's a bunch of cosines. They are weighted by 2, 3, 4, and so on and so forth. So you see the cosine gets narrower and narrower. So this makes this lobe narrower and narrower. And that only models very particular materials that follow this idea. But the thing is that it looks pretty realistic, and it's easy to compute. Yeah? And then we do something that is weird and absolutely nonsense, physically speaking, or it's not, it's not absolutely, but it's relatively nonsense. Let's say that there's situations where it kind of makes sense, but they're rare. So we add this specular term to this diffuse term. Okay, adding is always a bad idea when you don't weight things, because it means that you can go out of range. So this is why this idea of adding two terms is always a little bit sketchy, to say the least. So then the next thing that we do is we add yet another term. So do something even more sketchy. And what do we add? Well, we add something that we call ambient, and that's just a constant. You see, it's independent of pretty much anything. It's just basically the light source color times the surface color times the ambient surface color and the ambient light source color. And the idea here is that if we wouldn't add that term, then if these two terms happen to be zero, so for instance, if the light source is below the horizon, then diffuse and specular should be zero. Then we would get, well, zero out of this, because 0 plus 0 is still 0. So we don't necessarily want that. We don't want things to be pitch black, to be absolute black, but we say, well, kind of light bounces around, so any point is receives some light by some complicated process, by light bouncing off a couple of times. So that's it. This is why we add a third term. Okay, and then if we plug this all together, we basically get this here, this equation composed of these three terms. And here's a visualization of that. So if we add ambient, diffuse, and the specular part, then, well, we get something that looks shiny. And if we weight this differently, so for instance, if I would weight this specular down up to the point where I weight this by 0, then I would basically end up with this diffuse plus ambient, and then you can see that we actually interpret this different, right? So you would, if you just look at that, this looks like, I don't know, some cloth, maybe velvet or something, whereas this here looks like, I don't know, plastic or something wet. So this gives you some flexibility to create different virtual materials. So there's lighting. Again, should all be well known. The other ingredient that we need is, well, how do we transform things? And in particular, how do we transform normals? Because they apparently play a big role in this whole lighting process. Again, remember, this is our pipeline. Points are transformed by the model view transformation, plus then projection, and so on and so forth. And normals are transformed by the inverse transpose just of this model view matrix, and they are not projected. So for normals, we care about the actual three-dimensional structure, whereas for points, we want to project them right away. So the lighting, where does the lighting now happen? So the lighting happens right after those transformations. So once we've transformed the points and the normal, we would, again, we're talking about 90s style graphics here, then we would perform lighting. And then basically we can ignore the normals from that point on, because, well, all we used them for was to turn the light information, light source information, and the normals and position and a couple of other things into a color. And all we would do is then use that color in the rest of the pipeline, interpolate that color, and so on and so forth. Okay, so again, here's the image that I've also shown a couple of times already. So lighting is performed here right after the model view transformation, or the inverse transpose in case of the normals. And then from that point on, we're only dealing with the position that undergoes a perspective transformation and clipping and so on and so forth. And the normal then is just used to create a color, which is then interpolated across the primitive, which is usually a triangle. Okay, and that process, I said, is called rasterization or scan conversion. And well, what does rasterization and scan conversion do? Well, it figures out for a given triangle which part of the screen does that triangle overlap. So which pixels are overlapped by that particular triangle. And then it just doesn't figure out which one those are, but it also interpolates the values that are given at the vertices. So for this triangle, we have 3 values. Those could be, well, in the traditional pipeline, they're not normals anymore, but they're colors and, well, of course, position and maybe other attributes. And then those attributes are interpolated so that for each of the fragments here, fragments are the results of that coverage computation. For each of those fragments here, we then have a dedicated linearly interpolated color and position. Okay, so how is this executed? I kind of made this argument that it doesn't make much sense to care about how this works, because it's very machine specific. Okay, you could technically do it kind of the textbook old school way. So this is basically figuring out for each line on screen, for each pixel line, figure out where that line starts. Well, it starts on the left, but where does it not completely start and end, but where does it intersect the triangle? So where does it start in the triangle and where does it end? And in between, you simply output all fragments, and then you continue to the next line, and then you process those, and then you scan line by line the entire triangle. So this is where the name scanline comes from. But again, as I said, this is not how it's done today, in particular in hardware, but also in software. You have memory hierarchies, you have caches, and that makes it inefficient to really process this in a global fashion. You want to do this in a local tiled fashion, and so on and so forth. So it's sufficient to understand that somehow the hardware will figure out which parts of the screen are covered by the triangle. Okay, and that's assuming that we want to fill the object, but you might also want to render scenes in wireframe. Okay, so that's what I've shown here on the left. In that case, you would change the scanline approach here, again conceptually, not how it's implemented in hardware, but conceptually you would change it to a calculation where you just compute the entry and exit point and check where's the nearest fragment. Or where's the nearest pixel that this object overlaps, and to generate a fragment for that one. So this will give you a wireframe representation. What do you do when you have thick lines? Well, then it starts to slowly get a little bit more complicated. And but again, enough said, it's sufficient to interpolate along these lines, find entry and exit point, and do a second interpolation to figure the center point, or just use start and end if you want to do that. How do we interpolate? Let's just again conceptually repeat that. Well, how do we interpolate inside triangle, barycentric interpolation, or linear interpolation? Again, I'm not going to talk about these slides because I guess I've talked about them way too often already. So you should by now know how this works, except for the fact that it doesn't work this way. Okay, so what do I mean by that now? Well, all of this here, what I explained, obviously is correct. Otherwise, I would be a bad lecturer. But there's one thing that I haven't looked at yet, and that is what happens if perspective comes into play. So what do I mean by that? So this is all good and well. So we have 3 parameters. Let's get out of the way. So we have this triangle here. The triangle has 3 vertices. We have the 3 parameters that we want to interpolate. We can throw them into this matrix. We can solve that, and it's all good and well. But now something nasty happens here. And that is, well, we're dealing with, or we're at least often dealing with, a perspective situation here. So that means we have our triangles. Say, for instance, say this plane here is made up of 2 triangles. We have these triangles, but they are not just 2-dimensional triangles. They are tilted toward the 3rd depth dimension. And we have this perspective distortion that things, well, get smaller towards the back. Now here, again, I've rendered this quadrilateral. It should be a quadrilateral. And that quadrilateral is actually a square that is just tilted towards the back. Okay, and I've textured that with a checkerboard pattern so you get an idea how it works. Of course, I want to use only triangles, so this quadrilateral is made up of 2 triangles. And that's what you would expect. So if I would apply a checkerboard pattern as a texture to this object and to use that checkerboard pattern, I would do texture coordinate interpolation and then a texture lookup. You would expect this to look about like this here. So this is perspective correct. So this is accurate. Now, remember one thing about the pipeline, and that is we first transform everything. So we take our vertices, we apply the model transformation, we apply the viewing transformation, we apply the perspective transformation, we do the perspective division, and so on and so forth. So the rasterizer only works in 2D. So it doesn't know the full 3D information. It basically just knows 2D plus maybe a depth coordinate for each point, which in a sense represents a 3D. So if I would just take the coordinates of each of those two triangles and would do a linear interpolation in 2D, I would get something like this here. Okay, so you can actually see the two triangles that where the diagonal line is, and that's not what we want to see. Okay, so this is obviously not accurate. Okay, so what's wrong here? So why suddenly our interpolation that we've used all along, why does it result in texture coordinates that are not uniformly distributed, which then leads to a non-uniform distribution of the texture color values? Okay, so something is wrong here. So let's look at what's wrong. Let's simplify things a little bit and go 1D. Okay, let's say instead of having a 2D primitive, the square, let's say just have a line. Okay, because we can also see the problem on the line already. So this is my line here. So on the left, you see there's the imaging plane. Okay, so this here is our image plane. So here we've got this line, and this line extends in Z. Okay, so it extends into depth, so it's tilted just like our plane. Now, let's just look at what happens if you see the projection here of the starting point. So that's the projection of the starting point, and that's the projection of the end point. I've just drawn these kind of virtual arrays here to show you where the project and how the projection works. Okay, so it's a projection to that point. It's a standard perspective situation. Now let's just take the center point on screen. Okay, so now, and as you can see, that's not the center point of the line. So if I interpolate on screen, for this point here, I would get, well, the average, the exact average, 0.51 plus 0.5 the other one. But that should correspond to a point about here, right? This is the center point of the line. So this is where I would expect the interpolation to give me the average of the 2 points. But since this line is tilted, I get something that is slightly off. And that's exactly the reason why interpolating in 2D something that is in 3D tilted is not correct. Now, how do we fix that? Well, let's go through the computation here, and let's use the intercept theorem, or in German Strahlensatz. Okay, so this is the intercept theorem. Basically tells you if you have two similar triangles, I mean, it tells you a lot of things, but among those things, if you have two similar triangles, then basically the ratio of pretty much everything is the same. So, and let's do this here. So what I added here in this image is basically just added a few numbers. So I said D is the distance to the viewing plane from the viewer. Okay, so any point on the viewing plane has as its second coordinate D. And the first coordinate is, well, then it's X or Y coordinate. Well, if you say this is up, down, we'd say Y, and then the second coordinate is then Z, or whatever you want to name it. Okay, so the first coordinate of this, of the top projected point, I just call it U1 and distance D. Okay, and then the second coordinate is, well, U2 and distance D. So it's some other value. Okay, and then there's the center point, and it has yet another U coordinate, which is, well, somewhere in between. It's exactly in the center, and it has the same distance D. And for our coordinates in actual 3D space, we can do something similar. So we've got A, B, and C, uppercase A, B, and C this time, and they also have Z coordinates, and they also have certain, well, X coordinates, certain, well, up, down coordinates here. Okay, and now let's apply this intercept theorem, and that basically tells us that the ratio between x1 and z1 equals the ratio between u1 and d. Okay, so the height coordinate and the depth coordinate, their ratio should be equal. Okay, so this is simply Strahlensatz intercept theorem. And then I can just solve that for x1. Okay, why I do this, we'll see later, because I happen to need exactly that. I can do the same for x2. Exactly the same, except that I replace the ones by twos, but it's the same thing. And then the same for the center point. And here, for some so far unclear reason, I've chosen to solve this equation for the z coordinate. I could also have solved it for x, right? I mean, then it would have looked the same, but I need that for z later on. Okay, so that's one. That's just intercept theorem, should be relatively straightforward. Is not what I meant to do, so we're not done yet. So now let's look at something else, a simple ray equation. Okay, so let's say, okay, this point US, this point location in the center, this is simply starting at U1, starting at the top point, and then going some distance towards the bottom point. Okay, so this is just a simple ray equation, right? And then one here kind of goes straight down from A to B, from lowercase a to lowercase b. Okay, we say we start at A, at its first coordinate, and then go down some S, and that S, well, what does it do? Well, it goes down in direction from from a 1 to 2. Okay, good. Now, what else can we do? Well, we can do, again, the same thing for the x and the z coordinate. So we can also follow sort of that ray here. So we follow that diagonal ray, and we get a similar thing, except that now t is our kind of interpolation parameter along that one. Okay, so, and I can give this any name that I want. Are the x's swapped? So the question is, are x and y axes swapped? So I mean, I can name the x's anyway. So you can imagine this image that I have here tilted down, and then it's okay. So I just call the one axis that goes up and down, I just say that's the first axis, and then the second one, I call this, well, the second axis. Okay, and I happen to name them here x and z because one is the first direction, right? And then the other one is simply depth. So that's why I call them x and z, but you can really call them any way you want. Okay, but just here in my notation, the one is x, so this is my first coordinate, and the other one z. Okay, because it's depth, and I should call this z because depth has a particular meaning, as we will see once I'm done with all this computation here. So now what will follow now? So far we used two very simple things. Okay, intercept theorem, Strahlensatz, and array equation. Okay, those should be trivial. Okay, so now what will follow next is just basically taking those equations that you see here, those 6 equations, and plugging one into the other in some awkward way until we get what we want. Okay, so it's all very simple mathematics here. We just kind of need to follow that. So the first thing that I want to do is I want to take I want to take these 3 equations here and basically plug one into the other. Okay, so I basically took the z term here, and that relates x to z and to d and to u, and I took this x equation here, and I took the ray equation at the top to express u, and then I plugged this all together and solved it for z. So see that this one here nicely fits in there. Okay, it fits into the x term. This one here fits into the bottom. So we would expect something like zt equals d times this thing here, which is, this thing here, okay, which is exactly what we got, d times this thing here, and divided by that thing here. Okay, so this is the equation that we get. Okay, now you might ask yourself, why are we doing this? Well, hang on for a second. So I take this equation now, and that contains x, uppercase x1 and uppercase x2, and conveniently we've got equation for those at the top as well. Excuse me. So what I'm obviously trying to do is, I try to figure out things about the interpolated point with relation to the things on screen. Okay, so I try to eliminate the uppercase things as good as I can. So this is why I now plug in for x1 and x2, I plug in their formulas at the top to get this thing here. Okay, so as you can see, this basically just blows up. Yes, this is life. Well, at least now, I guess if you watch the video on demand, it's not going to be. But at this point, mid-January, it's life. Okay, so that's it. We take these two equations here and apply them to this function here, and this blows this up even more. Okay, fortunately, this can be simplified a little bit, and then we get this equation here. Okay, so what do we do with that one? Well, we'll continue. Okay, so we take that one, and we're almost done. Okay, and we take our equation to interpolate zt, and yet again, plug those into each other. Well, effectively take the right side and set it equal to the right side on the left equation. Okay, and then we get this thing here. Okay, and then we're done pretty much, except that we want to simplify this a little bit. So if I solve this for t here again, I get this thing here. Okay, so why would I even solve this for t? Because t is our interpolation parameter that we're actually looking for. Okay, so t is the thing in 3D, and now what I've done here is I've created a relation between this t, the parameter s, which is the interpolation parameter on screen. So this is what the rasterizer will figure out, right? It'll figure out how are things related on screen. So now I have a relatively simple relation between the interpolation parameter that I actually need, t, in full 3D, the interpolation parameter that I have in 2D, s, and I haven't really gotten rid of the z's. So apparently they play a role here. So I can do, again, plug one into the other to get to this equation here. Okay, so take the equation at the top, at here at the bottom, and then I ultimately reach at this point here. So why is that now better? Well, this gives me zt, okay? So this gives me the actual depth value of the interpolated point. Okay, which is an important thing. So I want to know that. And if I compare this equation here now to, I would say, the regular interpolation, right? So this is how I would normally interpolate in 2D, right? I start at a point, right here, this red at the top. I start at a point, go into my interpolation direction s, or go some distance s into my direction to the other point. And what you can see here is that these two equations are almost the same, except for like a tiny little variation, and that is, I have to compute the reciprocal of the interpolation parameter first, right? I mean, notice that this equation here at the bottom is pretty much the same at the top, except that it doesn't interpolate the z's directly, but it interpolates 1 over z. Okay, 1 over z1 plus s times 1 over z2 minus 1 over z1. So that's exactly the same here, except that it's the reciprocal of all the z's. And then, once we've done that, we need to compute the reciprocal again. And those two do not cancel out. Okay, so what this tells you is that if to do a perspective correct interpolation of the depth values, you cannot interpolate directly, okay, but you can use the same interpolation parameter s, which is what we have in 2D, but you have to first compute the reciprocal of the depth, then do the interpolation, and then compute the reciprocal again. But then you'll get a correct result. Okay, so that's how you interpolate z. Z is a little bit special here. If I throw this again into my equation at the top for any other parameter, I will get this equation here. Okay, so I'm not gonna go through that process all over again, but you can easily repeat the process for any other parameter other than z, x, y, some other quantity, color, whatever you want, and you would get the following result. Okay, so what you see here is that what do you have to do when you interpolate anything other than z? We have to divide by z first, okay, and then divide by the reciprocal of your interpolated z, or multiply by it. Okay, of course, you could also multiply by zt. That will give you the same result. Okay, so it's kind of a similar thing. except for computing the reciprocal here, you have to first divide by the depth coordinate. So you divide P1 by its depth coordinate, P2 by its depth coordinate, then perform the interpolation, and then multiply by depth again. Okay, so, and then if you do perform that, you get perspective correct interpolation. Now, fortunately, all of this stuff is done by the rasterizer for you. So you don't have to care about this too much, except if you want to interpolate differently. Okay, so if you want to have some different interpolation, if you, for instance, want to interpolate on screen directly, you need to be careful that this is something that the rasterizer will automatically do with any value. Okay, it'll automatically take depth into account, divide by depth, and then multiply again. So you might have to, for some computations, you might have to undo that first. Okay, but perspective correct interpolation, again, for Z, simply reciprocal, and for anything else, you need to take Z into account. Okay, yeah, welcome. Well, it actually turns out to be a pain sometimes. In particular, as I said, there's situations where you don't want this perspective interpolation, where you just want linear interpolation. And then it might be mind-boggling. Why is my code going wrong? So there's situations where you see this pre-multiplication in actual shader code. Okay, nonetheless, that's what happens. But that has to happen, otherwise your interpolation will not be accurate. Again, another repetition. What's the difference between this Garot and Phong shading? So what I've explained so far, like again, 90s style rasterization performs Garot shading. Okay, it's actually from the 70s, just like Phong shading, but the hardware implementation is from the 80s and 90s. Or well, for big computers, it started at the 70s. But anyways, Garot shading is this idea of, let's first compute the illumination. Okay, let's start for every vertex to compute the illumination value, to compute this Phong lighting, for instance. Get, in this case, for a quadrilateral, 4 colors and interpolate those colors, or for a triangle, 3 colors. Whereas Phong shading is this idea of interpolating the normal and then for each fragment to compute lighting. So this is what we would usually do today. And I'll show you examples in a couple of minutes of shader code that will do it exactly this way. But just, again, as a reminder, traditional rendering pipelines do the lighting computation in the vertex stage. And the reason is just performance. Okay, so you generally, or at least in those days, you had significantly fewer vertices than you had fragments. So it would make sense to do the interpolation, to do the lighting computation, which is relatively costly, on those fewer primitives. Today, this is kind of reversed. So first of all, we usually have a relatively detailed geometry that leads to very small triangles on screen. And that usually means that we tend to have more triangles than we have fragments. So it's more beneficial to do the lighting computation in the fragment or pixel shader stage. So that's one. And then second one is computation is pretty much free. What for modern processors with all their caches, with the RAM running at lower speeds than the actual processor, computation is relatively cheap compared to memory transfer. So this is another reason why today, with today's hardware, memory hierarchies, and so on and so forth, it doesn't matter anymore. So, and that's generally a take-home message. You can do just about as much computation as you want, unless you do really fancy things such as cascades of trigonometric functions or so. But in the normal situation, you can do as much computation as you want, as long as you don't access additional memory, and it will not impact your performance at all. So it's not just that it impacts almost not, it has no impact. The reason is that we have a pipeline. So when some fragment waits for data to come from memory, another fragment can do the computation in the meantime. So these computations overlap, and hence there's literally zero overhead. It's not small, it's zero, unless your computation is so costly that it takes more time before the data arrives. But that's a factor of a couple of thousands. So long story short, computation doesn't matter. And even if it would matter, it's actually better now to do it in the fragment stage. Okay. So here again, I've shown that image before. So this is what you get when you do flat shading, Gros shading, or Phong shading, all with the formula lighting. Okay, and as you can see, flat shading, here we only compute one color for each primitive, so it looks flat. Here we compute one color for each vertex and then interpolate the colors, and here we interpolate the normals, and it gets smoother and smoother. Okay, so the order increases. Good. Now, that's basically all I want to say about the scanned conversion thing. So the key component here is it does the interpolation, it does the coverage computation, so it figures out which fragments are important, which are covered, by the way, and it does this interpolation as a perspective interpolation. So those are kind of the three take-home messages here. So now let's look at the next part of this pipeline, the fragment processing stage, and again, sometimes referred to as pixel processing stage here, which is completely stupid. Thank you, Microsoft, for calling it the pixel shader. Okay, so we should call it the fragment processing stage. So what happens here? A bunch of things, and one big thing that I put here at the top are textures. I talked about those before. I kind of try to like literally set this idea on fire that a texture is not an image stuck to a surface. That's what you would think, what most people think, but this doesn't work very well. So you should really think about a texture as a lookup function, and that's usually discretely sampled in case of an image, but it doesn't have to be. Okay, here's again my motivation. Why do I insist that a texture is not an image if it works so well? Right, quarter letter on the left. We use this Lena image here with those texture coordinates, 1/4 and 3/4 as texture coordinates, and voila, we get this part of the Lena image on a surface. So why does it not work? Well, it fails if you do things such as 3D textures or 1D textures or any other fancy texture computation. Then this analogy will simply fail. Because, well, how do you put a three-dimensional cube on a surface? It doesn't work, okay? But if you think about this as a function, it's just a cross-section through the cube. So it's easy, okay? So, and remember, texture coordinates are specified along with the vertices. So this is very old school, excuse me. This is very old school OpenGL here, which you shouldn't do these days, but it still kind of symbolizes, and it's shorter in terms of code, so that's why it shows it. It symbolizes that for each vertex, I specify a texture coordinate if I want to, okay, or I can't specify. So in this case here, I've chosen 3-dimensional floating point texture coordinates for each vertex, right? If you use more modern OpenGL, well, then all of this would be hidden in arrays, but or in buffers, in buffer objects. But it's still the same thing, right? It's a stream where these texture coordinates come in. I talked about this issue of wrapping, what happens with texture coordinates out of range. We specify certain ways how to treat this: clamp, repeat, mirrored, repeat, border. So there's a couple of those modes. And those specify what happens with the interpolated texture coordinates when I look them up in the texture. So all of this is done again by the graphics card. So you just tell it, okay, here's the texture, here are my coordinates, those are my border modes, and you get a result out of that texture map. So again, that's very convenient. So it's kind of like an array lookup with this twist that your coordinates can be out of range and they will be handled how you want it. Okay, so this is all very convenient. So I think that I haven't talked excessively about, I mentioned this briefly, but I haven't really talked about this in detail, is what happens if, well, my object on screen is relatively small compared to the texture or relatively large compared to the texture. We call this minification and magnification. Okay, so, well, first of all, you could say, well, okay, why should I care? I mean, if I think about the texture the right way, namely this, it's just a function, a discretely sampled function that I look up, well, then, yeah, it's no big deal. We just, for the small version of our say, quadrilateral here, we just end up with relatively few interpolated fragments. They all have their associated texture coordinates, and we will simply look them up in the texture and we get the result as you see here on the slide. If I blow this up, if I make my quadrilateral fairly large, larger than so that it covers more fragments than my original pixels or texels in the texture, then, well, I'll have a ton of pixels. I'll have a ton of pixels covered. I have a ton of fragments, and those will just do their lookups. So yes, this will work. The question is just, what happens? How do I perform this lookup? Okay, and here this is shown in the center. So each of those fragments will have a texture coordinate, and that texture coordinate will usually end up being in between some of the pixels, or we refer to them as texels in a texture. It'll usually end up in between the texels, right? It's very unlikely that we'll have a coordinate that exactly hits a texel position. So we'll usually end up in between 4 of those. And the question is just how do we figure out what the value is? I already talked about the situation that I say, well, okay, I can do nearest neighbor lookup. So I can basically just, if that's my point, I could pick this one here. Okay, so we had this before. Or I could say, okay, well, we've got those 4 surrounding values. So I'll just pick, I'll just compute an average of those 4. And that average should depend on the position. Okay, so we call this bilinear interpolation. And again, that was covered before. Now that works, what's the effect of that? Well, if we use the nearest neighbor interpolation and we do magnification, we'll see blocks, okay? So we'll actually see the larger we make, the more we magnify this, we'll see blocks. We'll see the actual pixels in the texture. If we use nearest neighbor interpolation, this will be smoothed out. So we'll get some smooth behavior. Again, I've shown that before. Remember the colorful checkerboard pattern that I used. And that's all good and well. But what I want to talk about now basically is what happens with minification, okay? So let's look at how our sampling patterns are distributed, okay? So in magnification, what happens is that if I take all of my fragments, take their coordinates and plot them in the texture, okay? So this is a little bit mind-boggling. So let's just hold on here for a second, okay? So I take every fragment. We have a ton of fragments. We magnified the image. So we have a lot of fragments on screen. And each of those fragments has texture coordinates and looks those texture coordinates up in the texture. So now what I do here is I plot all those lookup points, okay? So if I do this, then I'll have very small distance between the samples, right? Because I do so many, I magnify this so much that I actually get a relatively small footprint. Okay, so if I zoom in, I just look at a small area, but in very much detail. Okay, so this can be a little bit mind-boggling because I say magnify and my sampling area shrinks. Okay, but it doesn't make sense if you think about this for a second. Okay, so and here again, here it makes sense. Like if I now have so many densely sampled pixels, instead of just saying, okay, well, this one gets assigned to this point, that one gets assigned to this point with nearest neighbor, I say, okay, well, interpolate this so to get different values so it doesn't look blocky. Okay, great. Now let's look at the other situation. Let's look at minification here. What happens when I make my object very small on screen? Okay, that means that the values for each of those few fragments will be relatively largely spaced in the texture, right? I mean, in the extreme point where everything falls into a single fragment, right? My object is super small, it just covers a single pixel, so I just generate a single fragment. Then I only have one sample point, right? I can only give this one color. So let's say, well, it's a relatively high resolution texture, but the object is pretty small. It's just only 4 by 4 points. Then this is what we'll get, right? We'll get 4 by 4 points, and those are very far away in the texture, okay? So again, we minify the things, but that makes our sampling area very large. Now, what this means is we now have these 16 points here, and I've also drawn in the pixel. Like every fragment corresponds to a pixel, and this pixel would have, I don't know, that size as you see here if I would basically take the 4 corner points of the pixel. So what now happens is that each pixel covers a ton of texture values, and then just taking for any pixel, either taking its nearest neighbor or taking its 4 neighbors is is pretty much both pretty a bad idea, okay? Because the pixel covers this large area, and then whether from this large area, which is potentially, I don't know, 30 pixels, whether I choose one, the nearest one, or whether I choose the linear interpolation of the 4 nearest is both pretty bad. Again, take the extreme point, this shrinks even further to 1 sample point. So I have my texture that might be, I don't know, 1000 times 1000 pixels. And I just choose one pretty much random pixel where my fragment is, or I choose the 4 around it, it's both pretty much as bad as it can be. So it's pretty much a random value. Okay, so for minification, if you choose linear interpolation, right, this basically or you choose linear mode, which corresponds to bilinear interpolation for a 2D texture, okay, or whether you choose nearest doesn't make a difference, or doesn't make a big difference. It both doesn't work very well. Okay, so here you see the result. If I choose this nearest neighbor interpolation, it gets blocky in magnification situations, and it's smooth and linear. Okay, but towards the back you get the same result. Okay, so you basically get garbage out of this. All right, look closely. You see all kinds of awkward patterns here emerging. So you get circular patterns, you get straight lines. It kind of looks weird, and this is, well, because it doesn't make a difference it does make numerical difference, but it's both bad. Okay, so what should we do? Let's think about this for a moment. Let's say we could do whatever we want. Okay, what we should do is in the situation where we minify the object, we should figure out, okay, what does each pixel cover, right? I mean, that's a certain amount of data. As you can see here, the blue pixel, it covers a ton. And then what we would want to do is we would want to compute the average of all those fragments, right? So the bigger our pixel would get, we would compute the average over a larger and larger area. And again, in the limit where our object is just 1 pixel in size, but get textured with the entire texture, I would want this to have the average color of all the pixels in the texture. Okay, so that would kind of make sense. Now, the trouble is that this is well, pretty costly. Again, think about a texture 1000 by 1000 pixels. It is applied to a tiny object that we don't even really see. I mean, just one fragment on the screen. With modern screens, this is so small you probably can't perceive it. But I would have to compute the average over 1000 times 1000 values. Okay, which basically means I would have to compute the average over 1,000,000 values just to color a single pixel. Okay, and the nasty thing is I would have to do this at runtime. Right? Because only at runtime I know what the pixel covers. Maybe it covers only half of my texture because I still have a 2 by 2 region. Okay, then I would have to repeat that computation. And then if I shift it slightly, so if the camera pans a little bit, for instance, or the object moves a little bit, I would have to repeat this computation. So long story short, this doesn't make much sense. I mean, from a sampling point of view, yes. From a numerical or computational point of view, no. Because for very small things, we would have to do a ton of computations, and it would take forever, and it would probably not have an impact that would make it worth. So what happens is that to speed this thing up, we try to use a different approach that results in a similar result, but is a lot faster. And the idea here is, okay, what can we do? Well, we could take our texture here, which is obviously a checkerboard pattern in this example here. We could take our texture, and that has a certain resolution. So let's say 1000 by 1000 pixels. Okay, so, and I take that and I subsample that. So I create a second version of the texture, just 500 by 500. And I create a third one, 250 by 250, and so on and so forth. Okay, so until I end up with 1 by 1. Okay? So I basically create a sequence of images that are the original texture, but subsampled by, say, a factor of 2. And important is I do this as a pre-processing step. So I don't do this in every frame. So this generation of this hierarchy, I do this once and for all. So sometimes this is even pre-computed. So it's not even done at startup time. It's actually stored as an asset on disk or in memory. Okay, and we call this thing a mipmap. Okay, so here's an example. of a space station here. It's a mere space station. You can see the original image on the left. You see a quarter of that image, so subsampled by 2. 2 in each direction makes a quarter in total. Again, subsampled by 2, subsampled by 2, until we end up at a 1 by 1 area. And you could try to fit that into a rectangle, and you would see you would potentially waste some space, but that's just the visualization. It's actually dense. To show you for an RGB image why you can nicely fit those subsampled versions, I've actually broken this down into a red, green, and blue channel. So if I take an original image that is maybe, I don't know, 16 by 16 pixels and take its red, its green, and its blue channel separately, then you can see that the rest of the image, so all of the subsampled versions, right, they perfectly fit into the last quarter. So what this tells you is that for a 3-component image, this entire hierarchy consumes actually slightly less, 1 pixel less than a quarter. So this doesn't blow up the data by a humongous amount. Okay, so it basically blows it up by 1/3. Okay, so, and it would fit, you could actually store that. If it's just red, green, or blue, you could store this in a rectangle. If it's red, green, blue, alpha, you would have to store this differently. But as you can see, it's not a huge overhead. Okay, so we can actually afford to do that at the beginning. So now, what do we do with that? So, okay, how do we use this map, this MIP map? MIP stands for multum in parvo, by the way, so it's Latin. So a couple of things in one location. So what this means is, what we have to do now during runtime is, when we want to compute the value of a specific fragment, we do 2 things. So we interpolate the texture coordinates, and that's all well. And then we have to figure out, okay, which one of these versions do we use? Okay, do I say I have point 0.5, 0.5, which would be in the center? Do I use that point here, or this point, or that point, or that point, or that point? So what should this depend on? Well, it should depend on how big is my fragment on screen. Okay, so what I basically do is I figure out how big is my fragment. Question is, how do I figure that out? More on that in a second. How big is my fragment? And then I use its texture coordinates to look into one of these maps. So basically, the size of a fragment will compute some offset in the texture map. But again, this is conveniently done for you. If you do that, okay, now look at this here. This is linear filtering, and this is this MIP mapping filtering. What you get is, towards the back, everything will be washed out because you get more and more interpolation. Right? You use smaller and smaller version, but you don't get these artifacts. And in particular, if I would animate that, I should probably add this to my slides, add a little bit of a camera animation. You'll see that this here would flicker, whereas this here stays still. I mean, it's washed out, but it stays constant. So that's a big advantage of that one. So the remaining question is, how do we figure out what the size of a fragment is? I'll talk about this in 2 weeks in more detail when I talk about sampling a little bit more. But just to give you kind of a quick pointer to this, what I can do is I can, instead of looking at each fragment separately, just for the lookup purpose, I can take the fragment and take its neighbors, left, right, top, bottom on screen, and check their texture coordinates. And then from those deltas, so what are the distance and texture coordinates? From those deltas, I can figure out how big the fragment is. So it's actually a pretty simple process. It breaks the parallelism a little bit, right? I mean, because now suddenly fragments have to talk to each other, which we try to avoid as best as we can. But here it's actually useful to process a couple of fragments together and then compare their results to figure out how big a pixel is. So that's an easy way how to do this. Okay, so why can't I just use depth? That's the thing that you might ask. Isn't size just depth? Well, not really, because what you have to take into account, in particular for if you want to do something that's even more sophisticated, which is called anisotropic filtering, you need to consider the tilt of the object. Okay, just because something has a certain distance doesn't necessarily mean that its distance to its left-right equals its left-right equals its top-bottom, right? So the left-right top-bottom neighbors might be different if the object is tilted, which it is in this case. So in that case, it's better to actually look at the neighbors. Okay, but details are details in 2 weeks on that one. So just to give you a kind of a head start, you would usually look at the neighbors to figure things out here. Okay, so that's the texturing. Okay, again, texturing is usually computed in the fragment stage. Today, with again more than a few minutes in shaders, you can also do texturing in the vertex stage, but you already see that the texturing in the vertex stage is a little bit different because, for instance, there's no such thing as MIP maps or no natural MIP maps. So it'll work a little slightly different, but so let's stick with the simple idea for this moment. Let's say texturing happens in the fragment stage, then we use all of that information that we have so far. We use the perspective correct interpolation. We compute the texture coordinates through this process, this perspective correct interpolation. We look them up in the texture. If we want to use a MIP map, we compare the neighboring fragments texture coordinates to perform that lookup, and then figure out which MIP level to use, which resolution to use. Okay, so once we've applied the texture, we're almost done. We're almost done with this pipeline. So there's just this one part, last part, that was called fragment tests and operations. Okay, so here's a breakdown of what OpenGL and DirectX does before a fragment can eventually become a pixel. Okay, so there's a couple of tests. So there's so-called scissor test, alpha test, stencil test, and depth test. So those are, as the name implies, all tests. So they can go, they're Boolean. So in a sense, either they go, they succeed or they fail. Okay, that's what a test does. It's a binary thing. And then something called blending happens, dithering, and then another bunch of logical operations. So I want to focus on 4 of these stages. Okay, alpha, stencil, depth test, and blending. So I want to skip the others. If you want to know the details, you can look them up in the OpenGL or DirectX manual. The reason I skip them is because they are only used in very rare occasions. So scissor test is, well, is used rare. Let's not go into too much detail here. And dithering, again, is something that you also only need in very rare situations with very low color precision, as are logical operations. So they are very specific to operation that we might consider in advanced image synthesis the next lecture. Okay, so let's first look at these 3 tests, alpha, stencil, and depth. And one of the really bad things about them is that they're named alpha, stencil, and depth test. Why are they named this way? Because the alpha test is usually used to test something against alpha. Stencil test is often used to do some stenciling, so stempeln in German, okay? So to cut things out. And the depth test is usually used to compare something to depth. The key here is usually, okay? So that means that yes, most of the time, but not always. It's just like with the textures, where most of the time you get away with an analogy of sticking an image to a surface, but not always. So let's explain them a little bit differently than just saying this is alpha, steps, and depth, stencil and depth. Okay, let's start with the alpha test. And another warning here, alpha blending is yet something different. Okay, so just because they got alpha in their name, it doesn't mean they're the same. Okay, we will have blending later on. Okay, so what I would want you to remember about the alpha test is not so much the value alpha. What is alpha anyhow? Okay, let's just go to the next slide. Alpha is usually another scalar that we send or that we can send along with a red, green, and blue component. So it's just a 4th component. Okay, and it doesn't have anything to do with transparency, please. Okay, that's one of the things that I'm very picky about. Yes, it's sometimes used for transparency, yeah, or opacity to be precise, but again, not always. Okay, and if you think about alpha as opacity, which is the opposite of transparency, you again limit yourself to a very small number of effects. So just think about alpha as another number that you can send along with a pixel and just happens to be called alpha. Okay, now back to the test. So what does this test do? And what's important about this test is not so much alpha, well, it's just a name for a number. What's important about the test is that it compares a fragment parameter against a global reference value or constant. Okay, so and the test itself can be something like greater, less, equal, not equal. So they're just a simple simple comparisons operation. Okay, so that and you can set them all. So let's forget about them. It's just a test of two numbers against each other, and they can be true or false. But the key is here again. The key is we take for each fragment its value and compare this to a global constant. Okay, so what this means is that first of all, for the alpha test, I have to set one constant. Okay, I said 5. Okay, compare this against 5, or compare this against 42, or 0, or minus 20, or whatever I want to set. Okay, so that's my reference value. And the fragment itself has control over whether it passes or fails the test. Okay, so when in the process of the fragment computation, it sets, let's say my reference value is 5. Okay, so and the fragment computation results in its alpha value being 10. Then for a greater test, it would succeed. And when the fragment computation results to a value of 1, it would fail. What does it mean, fail and succeed? Fail means the fragment gets deleted. Succeed means the fragment continues and maybe survives the other test as well and will ultimately be on screen. So long story short, the fragment computation can determine whether it wants to be kicked out or not by this test. Okay? Very important thing. So the fragment can selectively delete itself. So that's basically what the alpha test is good for. And it has nothing to do with transparency. Okay, you can say something that is close, delete it. Something that's far away, delete it. Okay, no problem. Just write the depth value into the alpha channel and you're good to go. Okay, so that's the alpha test. Again, take home message is global constant called reference value, global constant again fragment value. Okay, alpha test. Next test, stencil test. Okay, it's almost the same, except that now a global reference value is compared against the pixels value. Okay, so really, never mind this part here. So this just says that after the stencil test, the depth test follows, and they're kind of connected. So this is why I put them on the same slide here. But the key here is really only this one word here that changed, pixel. Okay, so and that's why I think that the tests named stupid are named stupid or stupidly because, well, one is called stencil and the other one's alpha because one uses the stencil buffer and the other one the alpha buffer, but that's not the point. The point is the stencil test compares a global reference that you can set. So there's an OpenGL call, there's a DirectX call, okay, reference value set. It's one value for entire screen. Okay, it compares a reference value against the pixel value. Now, what's the difference between pixel and fragment? Now, it's again important to know that there's a difference. Again, thank you, Microsoft, for screwing this up. Okay, so a pixel is something on screen. It's a point on screen. It's an array entry on screen. The fragment is the output of the rasterizer as it goes through the fragment stage and then ultimately wants to become a pixel value. Okay, big difference. So now here we compare the reference value against not the fragment, but a pixel value. So that said, a fragment does not have an influence on whether this test passes or fails because none of its parameters is taken into account. Okay, so what does it mean? Well, you have a on top of the red, green, and blue pixel mask that you see on screen, you also have a depth mask and you have a stencil mask. So basically what you do before you even start to render, you set some of the pixel values to certain stencil values. And then you start to render. And no matter what your fragments do, no matter what your computation does, none of that computation influences whether the fragment is ultimately visible or not. Okay, so that's the key point. And here are examples how this is used. For instance, I can render two scenes. Okay, so I've got two scenes here. I got this scene here and that here. And I render them one after the other. So I first render that one, just normal, on screen, but don't show it yet. Okay, and then I render this screen here, this scene here on the screen. Okay, so that would usually override that one. Okay, if I clear everything else except color buffer, this would override and we would not see that first frame. Okay, but I set the stencil test, for instance, for every 100 pixels, I set the stencil value, I toggle the stencil value between 0 and 1, okay, here. And then I say I set the stencil test to be equal to 0. Okay, and that would mean only where the stencil value is 0, the second scene would be drawn. And again, regardless of what the computation of the scene is. So I only want this to be dependent on the pixel position. Then I could create this pattern here, or I could, with a brush, actually let the users paint into the stencil buffer, and that would have the effect that it looks like as if they're scraping off one scene from the other. Okay, so it sometimes makes sense to say, okay, well, I want this pixel to come from there and then that pixel from there, regardless of this here, what this here and there, what it does. Okay, so that's the stencil test. Okay, just to scare you a little bit, so this is what this would look like in traditional OpenGL code. Okay, so it's a pain to say the least. Okay, so but once you get used to it, it's okay. So those buffers are things that you can clear on top of the color buffer that you can clear. So I would draw image 1, then I would say set specific draw mask, I would enable the stencil test, I would set it to certain parameters, I would then draw my stencil pattern, so that would basically change the stencil values, and then I undo a bunch of things, and then I would do my function here, and the key is really only that one here where I say, okay, only draw the second scene where the value is equal to 1. Okay, and then I draw my second scene, and that would, again, basically create this effect of this brush or checkerboard pattern. Okay, but this is just a side note here. Again, if you want to implement that later on, you'll hopefully have some code to look at and some guidance or books, because this is really a little bit of a pain to get it to work because of all those state changes. And we'll see in advanced image synthesis that due to the fact that there are so many state changes involved in dealing with the stencil buffer, that it's often implementations try to avoid this. So the reason why I'm mentioning this is that it has an actual implication on today's rendering approaches, because programmers try to avoid using that functionality because it's hard to code, right? They're simply not good enough to deal with it. So that's it. And we'll actually see that. We'll see that in advanced image synthesis. It's something that some algorithms that are actually good, deliver good results, are fast, high performant, but they involve complicated coding. And even in commercial engines, they are avoided for that reason. It doesn't mean all programmers in commercial software are idiots, but it's just very hard to get it right. Okay, and that's why you often see stencil, for instance, stencil shadows being avoided. But long story short, that's how the stencil buffer works. So it's a global reference against the pixel. Alpha test is global reference against fragment. So what's left is pixel against fragment, and that's called the depth test. Okay, and again, the name is misleading. It doesn't necessarily have anything to do with depth. You can use it for depth, right? Perfectly fine, but you can also use it for a million other things. So what it does, what the depth test does, it compares a pixel value against a fragment value. Okay, and again, the comparison is less, equal, greater than, less, less, greater, doesn't make sense. Less, equal, greater, equal, all these things. Okay, so we now have 3 tests. One test, fragment against reference, called alpha test. One pixel against reference, called stencil test, and one pixel against fragment. So each pixel gets tested against its corresponding fragment, or the other way around. Each fragment gets tested against its corresponding pixel. And we call this the depth test or z-test. Okay, but again, you can use it for other things other than depth. You could do an alpha test by just, in your fragment, just say fragment point z equals fragment point alpha. Voila, you copied your alpha value and your z value, you enable your depth test, and suddenly you get something that is based on alpha. Okay, so very misleading name. But nonetheless, let's see how this works. Let's see what the whole point of this fragment against pixel is, because here we got an interesting twist, and that is, well, we compare a pixel against fragment. Okay, good. But once the fragment passes this test, it overrides the pixel, right? I mean, that's the whole point. A fragment overrides the pixel when it succeeds in all those tests. So the interesting thing is that one fragment can then influence the next fragments, because it now is the pixel. The pixel is tested against the next fragment. So what the depth test allows us is is much more powerful than the previous test in that now we can have dependencies between fragments. We can have influences between fragments, which we cannot do before because they're all processed independently. Okay, and this is why it's also called depth test, because it's often used to resolve the occlusion problem. What's the occlusion problem? That is, we only want to see the most closest object. We only want to see the most nearby object and nothing else. And that, unfortunately, is a global question, right? What's the closest object? Well, that is something that depends on all objects, obviously. Okay, so how is this resolved by this depth test? And the idea is, let's just assume that's not how it works exactly, but let's, for simplicity's sake, assume that I've cleared the depth buffer with infinity. Okay, so and I've got something in there already. So I got a yellow triangle there with depth 2. Okay, and closer means smaller means it's closer. Okay, so now what I want to do is I now want to render another triangle, a blue triangle that has distance 7. Depth 7. So they're all perpendicular to my viewing direction, again, for simplicity's sake. So what I basically have, I have this structure here. So those are all the fragments that I generated. Well, then some of those fragments should be visible, and some of those should be covered by the 2. But the question, the ones with depth 2. The question is, how do we deal that? Well, we do this by comparing, for each fragment, comparing their depth values. For each of those 7, never mind the whites around that. For each of the 7, I compare it against the values. So some of those will get compared against infinities, and infinity is bigger than 7. So the 7 is written along with the color into the buffer. And some of those are compared against the 2s, and 2 is smaller than 7. So we would kill those fragments, and we would end up with this result. Now, if I would render another triangle with depth 5 and in green, say this one here, it should end up between the 2, right? So, and again, if we compare each of those 5s against the value, some of those would overlap 7, some of those would overlap 2, and some of those would actually overlap infinity. So we would get this here as the final result. And the cool thing about this whole z-test or depth test thing is that regardless of the order, so if I would just swap the order around, I would have first rendered this one here, and then the 7, and then the 2, or whatever order, I would always get the same result. Okay, so and that's very important because we don't want to control the order of triangles. Okay? If we send them in some random order, and then we, for instance, even if we would depth sort them, but if I would turn the camera around, the depth sorting would be wrong, right? So we don't want to repeat this sorting, or we don't want to sort at all if it's possible in some way. So this is why we can use this test to figure out which is the closest object. But we could also, again, use it to figure out which is the reddest object, or the bluest, or the brightest, right? If we just write different values into the depth component. Okay, so, but most of the time, admittedly, the depth test is used to resolve this occlusion problem. Okay, so that's how this test works. Again, fragment against reference, pixel against reference, and then finally, pixel against fragment. Okay, those are the 3 tests. Now, what else was in stock here? And that was alpha blending. So that was another step, or just blending. Okay, it's sometimes referred to as alpha blending. And again, there's this naive idea, it's like, oh yeah, enable alpha blending and we get transparent objects. Nope, no way. Again, very important distinction here. So what the blending stage does, and again, I should probably also fire up alpha here, because it doesn't necessarily depend on alpha. You can set the blending to not use alpha. So, what the blending does, it's not for transparent objects. It can be used for a transparent object, but by the way, to do transparent objects, you have to do way more than alpha blending. You have to do a ton more things, more on that in advanced image synthesis. So actually the blending is the least of the problems with transparent objects. So, but what the blending does is it blends. Well, it mixes, that's what blending says. Instead of overriding the value that is in the pixel, what blending does, it allows you to specify a function that says, okay, don't just override this, do take the pixel and the fragment value and combine them, blend them together into one new value. For instance, add them up, right? Or subtract them from each other, or multiply them from each other, or XOR them for that matter, okay? So those are all things that you can do. So alpha blending allows you to specify a function that takes 4 parameters total. Well, 5 to be precise. One is the operation, plus, minus, XOR, and whatever. right? It could be just arithmetic operation, but it also can be a logical operation, bitwise logical operation. So, and then the other 4 parameters it takes are what 2 things should we combine and how should we weight them. Okay, so you can say fragment color plus pixel color, but the fragment color weighted with 5 and the pixel or with 1 and the pixel color with 0, which would basically say cancel 1 out, or take the color of the fragment and weight it with the alpha of the pixel and take the color of the pixel and weight it with 1 minus alpha. So there's a couple of things you can do. And if you're interested in the details, you can just look those up, what parameters you have. Okay, so here are the operators, maximum, minimum, subtraction, and again, those logical operations. Okay, so what blending does, it allows you to combine the value in the buffer with the incoming fragments. Be aware, and that's a very important warning about this test, is it's pretty dumb in a sense that it literally takes every fragment as it arrives, takes the current pixel value, like, okay, so we got those fragments arriving here, so you can assume they're streamed like one after the other, and you've got your pixel value here, and so you take the first fragment that's mapped to a pixel and you combine with the blend function. Okay, then suddenly another fragment comes that also happens to be projected to that pixel. So it now takes the computed new pixel value and combines it, and so on and so forth. So here order matters. Okay, so at that point, depending on how you choose your operations here, they're not associative potentially, okay, or commutative, and so order matters. And this is one of the nasty things about alpha blending or blending in general, that you then have to worry about the order of things. Okay, but nonetheless, blending allows you to combine things in the buffer with incoming things instead of just overriding them. So that's what it does. And here's an example. So for instance, if I take the intensity of whatever is in the buffer, so things that are high, that have a high value, that are bright, if I use that of a weight as a weight for a second image, okay, in this case a mandrel here, and I weight the incoming fragments of the second image with the brightness of the previous image, then what happens is wherever the previous image is bright, I see a lot of mandrel. Wherever it's dark, I don't see it. Okay, so and then you can create all kinds of fancy effects. Okay, and again, there's a whole science to what do we use alpha blending for to do fancy things. More on that again in the next semester, advanced image synthesis. Okay, and then we're done and we display the result. So that's it. One final remark for today, and that's also my final remark on the rasterization pipeline, is what happened since the late 90s, 2000s. So I've been talking all along about old style graphics. Okay, so why am I doing this? Okay, and the reason is the following. Of course, today we have programmable hardware, right? And I mean, I've at some point stopped to update this slide. So it's I think it's maybe we have, well, certainly we have newer graphics cards, despite the fact that suddenly you can't buy them because of chip shortage. But so we get newer and newer graphics card with more and more functionality, and now for about for 2 to 3 decades, depending on how you count, we have programmable shaders. We have programmable hardware, and you don't do graphics the way I explained it so far. Okay, so why would I do that? Why would I even bother tell you something that is completely outdated? Let me just quickly put the button here. Okay, the reason is the following. Because to do this super cool programmable thing, what you have to do is you have to program all of what I told you so far. Okay, so but then why do we have programmable shaders? Why do we have a programmable pipeline? What does it even mean to have a programmable pipeline? And the idea is that this fragment stage and this vertex processing stage, instead of just running through these fixed steps, we can write a piece of code, usually small code, but potentially very large code. I mean, there's shaders, we call them shaders. There's shaders that are easily 10,000 lines of code, so they can be pretty complicated. So instead of just running through these fixed steps, around the millennium, hardware changed so that it would allow you to submit your own code. And the reason was pretty simple. There were so many different options. So these fixed steps were so many that the manufacturers decided, okay, well, instead of just having all this dedicated silicon, let's just have some more open architecture, just like an ALU, and just upload microcode depending on what the user said. And then at some point, someone figured, okay, why don't we just let the user upload the microcode right away? Technically, okay? So in some higher language. So, and that allows you to do whatever you want pretty much within some boundaries of what the language allows you to do. So what do we have these days? We have programming languages, shader programming languages. They're called GLSL for GL shading language, used for OpenGL, and Vulkan. Vulkan there's no Vulkan shading language. It just uses GLSL. There's HLSL, high level shading language. That is what DirectX used. And there was also C for graphics from NVIDIA, which is basically the same than HLSL. I don't think it's still around. I think I guess NVIDIA still keeps the driver around, but it's basically been replaced by HLSL and GLSL. And those two are pretty much the same. So there are subtle differences in syntax, but functionality-wise, they're the same. They're all C style, or sometimes even C++-ish. So it's somewhere between C and C++, I would say. But let's just say it's C style. It's kind of an interesting thing how it works. So you compile the program usually every time you run your program, which is kind of unusual. Right? Usually you have a pre-compiled code, but here you compile it at program startup, either from source or from some intermediate representation, and then it gets linked and then ultimately run on the hardware. The languages themselves are pretty much hardware independent, except for, well, hardware dependent extensions. For instance, CUDA is an extension from, or CUDA is yet another language, which is still very similar, that is very NVIDIA specific, okay? But those general graphics languages, GLSL, HLSL, they're hardware independent. But what do they have? Data types, float, double, boolean, int, the usual stuff. If you know C or Java, relatively similar. But they also have vector data types, matrix data types, texture data types, we call them samplers, and they can do arrays and structs. So there's things that are in there that go beyond C, okay? You have operations, plus, minus, times, division, plus, plus, minus, minus, usual stuff. But the cool thing here is you can do a plus of two matrices or two vectors. It will compute vector and matrix arithmetic for you. You can do, you can access members of vectors or matrices by what's called a Swizzling operator. You can do comparison logical ops, the usual stuff, okay? Let's just quickly, because this is more like something that you would want to look up later on. Let's just quickly go over a few features of the language. One interesting thing is that it's not in usual C is that you can flag variables. You can say, well, that's the uniform variables. Okay, so normally at the bottom here, say you have a med for MVP. Okay, so this would mean, ignore the uniform for a second. That would mean that I declare a new variable of type med4, which is a matrix 4 by 4. And I call it MVP, which is supposed to be model view projection here, right? But in GLSL, for instance, like this is all GLSL, HLSL has similar concept. In GLSL, I can write uniform in front of that. And that means, okay, that is something that I have only said once. That's kind of a constant, a global constant, okay? And conceptually, that is something that you would have changed outside of GL begin, GL end, okay? So it's something that you said not per primitive, but that you said per scene or per part of the scene, okay? You cannot touch this in the shader. I mean, you cannot write it in the shader. It's a constant, okay? And the model view projection, a matrix, for instance, would be such a thing. You can also specify things as in. So if you have, for instance, in vec3 vpos, this is something that you expect as input from, if this is your vertex shader, that's input from the vertex stream. If it's in your fragment shader, that's the output from the rasterizer, that's your input from the vertex shader, okay? So you can, for instance, set in vec4 vpos, which is my short for vertex position, right? That would mean, okay, in this variable, I want the position of the vertices. Now the question is, how does the shader know where to store the position or where to store the normal or where to store the color if you can choose these variable any way you want? Like this vpos is just me, like literally me, my code. So I can also call this blah blah. How does the graphics card connect your stream to the names? Well, either by getters. So in your OpenGL code, you can say, okay, well, get me the names, and then Okay, tell me where is vpos located, and you get a number back. It's location 0, and then you can set, okay, location 0 should be position, location 1 should be normal, whatever. Or you can also specify this in your code, in your GLSR code, by this really awkward notation saying layout, opening parenthesis, location equals integer, closing parenthesis, and then the rest. So that says, okay, well, the first entry is this variable here, and then the first entry, well, it's a vec3, so the first three, every first three floats are interpreted as position. So this is how this works. There's also an out specifier, so this basically tells the code, okay, what's the output? And yes, that can also have such a location specifier if you have multiple outputs. So that's the same here. So for instance, if you want to write out a color in the vertex, in the fragment shader, that's what it would look like. Okay, you can do things like branches, loops. You'll have a main function. Any other function can also have its parameters specified as in, out, or in, out. For this, almost like call by reference here. You can have trigonometric function, exponential functions, geometry, cross product, dot product, length computation, normalization, all that stuff. None of that really makes much sense as long as I just dump it at you. You have to code this up to figure it out. And here's just an example. Again, this is more for reference at home. So this is an example vertex shader. So this is what it looks like. So it starts with a comment specifying the version number. Then I give it a few constants, model view projection, the model view, and the inverse transpose. Model view, not to forget that. I assume as input position, color, and normals from the vertices at location 0, 1, and 2. I write as output color, normal, and, well, a position. As output, technically I write 4 outputs. One is a special one, that's this GL position here. So that's a special variable that you always have to write to in the vertex shader, because that's what the rasterizer takes to compute the coverage. And what is the position? Well, it's the model view projection times our initial position, and I just add a 1 to do this in homogeneous coordinate. Okay, then I compute the position in full 3D. So I notice that I take my position and multiply this now again by the model view, not the model view projection. I'm only interested in the 3D version, so I truncate the W coordinate. The color, I just hand this through, so output is just like input. And the normal is, of course, the model view inverse transpose times the normal. But remember, I add a 0 to that one. And I'm also only interested in XYZ coordinates. Now that's my vertex shader. So that basically just transforms normals and positions and hence color through. And here's the corresponding fragment shader, which just computes diffuse lighting. Okay, so I will not explain this here for the fun of not doing it. And I want you to look at that at home to figure out why does that compute diffuse lighting. As a matter of fact, I took those 2 shader codes from one of the exercises that you were supposed to do. So those were the shaders that were executed in this very program, as you see here, to render that bunny, to render that result of your vertex computation. Okay, so or your shared vertex computation. Okay, so this were the actual shaders. So you can actually look, you got the source code, you look in the source code and you compare this to my previous slide. So it's one by one copied of that source code. Okay. So, but still, I want you to go through that code, try to understand it. If you have any questions, so it's probably the case that it's not entirely clear, then please ask in the exercises. Okay, please ask in the exercise. The exercises are also remote, where we do them in maybe a more conversational friendly way. I didn't have many questions, like 1 to be precise today. So to encourage more questions, we'll do the exercises more in a remote in a telephone conference environment. You should have received details about the exercise already. Okay, so that's it for today. So we'll end a little bit early, but I don't think it makes sense to start with a new topic now. Well, next stream, which if you watch it live will be next week, will be about how do these things scene graphs work. So, or in other words, when all this low-level program with OpenGL is such a pain, why go through it and why not do it in some higher level? And yes, this could be done. And that thing is called a scene graph or an engine. So engine is usually another name for a scene graph. Okay, so that's it for this stream. Do you have any last-minute questions about today's content? And you don't have to come with the questions right now. In general, I encourage you to ask questions throughout my stream. But if you have one, do it right now. If not, just do it if not now, do it in the exercises later today or next week or whenever. Okay, that doesn't seem to be the case. Then thank you for listening. And again, we'll have more on scene graphs next week, same time, same day. Until then, bye-bye, stay healthy.